Welcome to the circular motion unit, and that will be our topic for the entire unit. Today we are just covering speed and velocity, well, and a couple other things. So let's take a look at this nice circle that I drew for you. Could you please now label the center and draw a radius for the circle? So I will draw the center there, and you can draw the radius anywhere. I, by habit, kind of do it this way. Now it says, trace an arc on the circle that is approximately 1 radius. And that might not make too much sense to you, but if you think about the length of this radius here, and if you think about, okay, if I want to make an arc length that is about the same length here, pre-cal students might be thinking, hey, that's a radian, an angle of a radian. So that would be about how far perhaps 1 radius would get if I made it an arc along the circumference. How many radii to make 1 circumference? So what if I just kept on doing, okay, the next one would maybe go to here, the next one maybe till about there. So why don't you fill that out and consider how many we would get. 4, 5. Turns out, would we get, how many would we get? A bit more than 6. In fact, it would be pretty close to 6.28, which might remind you of something. It is actually, you would get 2 pi. That's exactly how many radiuses it takes. So if I was to wonder, what is the length of this circumference? If I was to say, what is the length of that kind of arrow that I just did, even though it's circular, the formula is the circumference is equal to, well, I need 2 pi radiuses. So there is a formula from back in the day. I'm sure you kind of remember that. So the next question, or the next part we're going to look at is say, well, our unit about an object moves in circular motion at constant speed. We're going to be looking at objects that are moving in a circle and are relatively at a constant speed. Another name for this is uniform circular motion. Here's a classic example. This is a Ferris wheel. So imagine if you got on and you were traveling up the Ferris wheel, and perhaps right here you'd been going upwards and so forth. Here, this is a roller coaster, and although you might say, Mr. Speiser, that's not a circle, you can even say, well, this portion right here is part of a circle. So we can actually take the stuff that we're learning and say, hey, for this portion of our roller coaster trip, we're going to be learning things that we can apply to that, and actually even this section here, because this was part of a circle as well. Notice that it seems to me that the radius of that circle, as you know, as the roller coaster would go through here, that radius seems to be larger than those. The hill has a larger radius than the troughs over there. Here's another example of a car that's going around a corner, kind of like the roller coaster idea. So the car is going around the corner. From here to here, it is actually a part of a circle. Okay, thinking about cars going around circles, you may have seen this section here before, and there's a bunch of physicsy stuff labeled on there about sometimes we actually bank the corner so that it can go around in a circle. This car would be going around in a circle, and the circle would actually be sort of that one, with the center would be way over there, even though it's at an incline. Here's another example of circular motion. I don't know if you've ever done this. You put water in a pail, and if you swing it nicely and fast, you can actually make it go all the way around, and it's kind of cool because the water doesn't hit you. Last, here we have a nice little sketch of a moon going around the Earth, and it is going in a really nice circular motion. Over to the other page. This is something that we may have already talked about in class. When we're looking at circular motion, what can we measure directly, and what would we have to do to calculate? So when I'm thinking about radius and circumference, well, if I've got an object here, I can just measure the radius. How about in this one? Let's say I've got a very large clock. Let's pretend this is a very large clock, and that this here is maybe the second hand. So there's the minute hand and the hour hand. This is the second hand. This one that goes around once every minute so that you can tell what second it is. And let's say that this large clock all the way across is, say, 1 meter. We'll keep the numbers pretty easy. So if I was to say, hey, can you figure out the radius? Sure, you could get your tape measure out and you could measure this radius here. And in this case, the radius would be 1/2 of a meter, wouldn't it? And if I was to say, what is the circumference? Well, you could sort of measure directly by maybe taking a string and making it over the circle and then putting the string onto a ruler and measuring it. But it would be a lot easier to actually calculate. So what are we measuring directly? Radius. What do we typically calculate? Circumference. And we're using that radius measurement we had. So what would be the circumference of this particular clock? Well, if the radius is 1/2 of a meter, it'd be 2 pi multiplied by 1/2 of a meter. So that would actually be, oh, that's kind of neat, pi meters long, which would be approximately 3.14 meters. Okay, that's kind of neat. What else could we measure? Well, if this clock is moving along, and I guess the second hand moves this way, doesn't it, as it rotates around, we could measure the period that it takes. So how long does it take for this second hand to go all the way around? Well, period is exactly that. How long? So usually we use seconds for one cycle. The letter that we usually use this is T for period, and it's a measurement of time. How long does it take for the second hand of a clock to go all the way around? In this example, it would be 60 seconds. Okay, so this is something that we could measure directly. How would we measure it? Probably with a stopwatch, right, or a smartphone watch, or just our knowledge of the clock would actually tell us it's 60 seconds in our example. So what about speed? Well, speed is an example here that we would actually calculate using this period idea. Speed is distance, how far something goes, divided by how long it took in time to do this. So if we consider one revolution, then the distance that it goes will be one circumference. And how long will it take? That would be one period. So in other words, the circumference, if you want a general formula for this, we would say the speed, and I'm going to use the letter V right now, even though it's speed, is going to be equal to 2 pi r divided by the period t. So in our example here, it would be 2 times pi times 0.5 meters, all divided by 60 seconds. So this 2 times the 0.5 is equal to pi. So really I get pi over 60 meters per second, which works out to, I don't know, approximately 0.05 meters per second. So we could get a speed, how fast it's going. We've got to be a little bit careful about this period and speed, because sometimes we can get a little bit mixed up on them. And I'll just do a little bit of an aside on this one here. Let's pretend that there are 2 bugs on this second hand. Okay, I'll put a bug A is here and bug B is over there, right? And I'm going to start 2 sentences here. I'm going to say A and B have the same ... and A and B have different. So when you think about the path that A takes, A would be going like, around this part, and B would be going around in basically a smaller circle. So what do they have that's the same? Well, they are going to be taking a lap in the same amount of time. So really they have the same period. So someone might look at that and say, A and B have the same speed, they go around the same. Well, kind of. It's the same period. If you want to get really technical, you could call this, and we don't do this in high school usually, but in university we take something called angular velocity. So they do have the same angular velocity. The units for something like that could be either degrees or radians per second. That looks like a percentage sign, doesn't it? Degrees per second, or probably more likely, if you're in university, you might be doing radians per second, would be the units for that. So you could say they have angular velocity that's the same. In other words, they're doing 360 degrees in 60 seconds. That's the same amount. But for our purposes, we can just say that they have the same period, and we won't worry about that. What do they have that's different? They have different speeds. Which one is faster? A would be faster than B. It has a larger circle. Their circumference is larger in the same amount of time. All right, let's talk about velocity here. We're almost done. Well, if I consider again that same clock, so again, we'll say that this is rotating clockwise, and if I'm at that 3 o'clock position, what direction am I going? Well, I would be going straight downwards. If I was over here, I would be going straight this way. Okay, how do we figure that out? Well, the velocity. Let me just back up for a second. I'm going to just say the difference between speed and velocity in case you guys forget. Velocity is a vector, so it has direction. Speed, no direction. So really, we already figured out how fast it's going. When I'm bringing up the topic of velocity, I just want to add now which direction is it going. So the answer really is, when we look at this, and if I draw the center, and if I draw this radius, you'll know that the direction that it's going through that spot is the same as the tangent to this. So what is a tangent? Tangent touches a circle or a curve at only one spot, only at that one, or I'll say point, better word, only at one point. The other thing about the tangent is that the tangent is perpendicular to the radius. So you'll notice that this is 90 degrees here. So if I was to ask you, well, what about, say, at this spot over here? You could say, well, if I, in my head, kind of draw that there, and I say, okay, the tangent is perpendicular to it. And then you say, well, which side of the arrow? Well, if I'm going clockwise, then I'm really saying that the velocity would be this direction, or trying to draw a straight line, that direction, that would be the velocity at any point. So the velocity, the big idea is tangent to circle. All right, almost done here. It says, which way will the ball move when it exits the tube? So I imagine this is a little golf ball, mostly because I like golf, and let's say it's shot inside this tube, which is curved somehow. It goes in this way, and then it's caused to curve, and then it shoots out here. And the question is, when it leaves the cube, or it leaves the tube, which direction is it going? And I think we have to make an assumption. I think we should assume that the forces are balanced. So we're going to say F net equals 0 when it exits. So we're kind of like looking overhead right now, and this whole thing is on a table. So it's not like the floor is here and it's going to fall like that. That's not what we're saying. We're saying that this is on a table, and when it comes out, F net is equal to 0. So what do you think? Which way would it go? Well, this whole F net equals 0 thing means that it's going to continue to move in whatever way it was moving. So my question is then, right here, how is it moving? It's really about that whole tangent thing. We're going to say at this point, it would be moving this direction. So how would it move? It would just continue. How about if I do a little motion map? It would just continue to move in that direction at a constant velocity, right, until some unbalanced force acts on it. So it would continue to move that way. All right, there's a short speed and velocity worksheet and a Minds on Physics to work on. I will see you in class.